Hello, my name is Adam Tyson, and I'm here to share with you guys all that I know about quick sorts. So let's get right into it. So the quick sort's its purpose is to go where no man has gone before, and that is the only Star Trek joke I will make throughout this whole presentation. Its actual purpose is pretty simple. It is supposed to be an algorithm, a sorting algorithm that uses the divide and conquer technique to essentially sort whatever sort of data set that you want sorted that you'll give it. The main benefits of using quicksort, because there's so many sorting algorithms out there, merge sort comes to mind right off the bat. What makes quicksort a really good algorithm to use for sorting is that it is quick, it is really efficient, it is really good at for large data sets, and that is mainly due to the average performance that you'll get out of quicksort. And I'll go back to that here in a second. And that is very flexible. It will take in it'll take in various sorts of data types, not just numbers, not integers, not just floats, but also strings and others, and whatever else you'd want to throw at it. It is very flexible, and you can adjust that to however you wish. So moving on. Quicksort and how it works. So, like I said, it is a divide and conquer algorithm. And you'll see the second point that I have that says pivot and partitioning. So I'll get to that here with this diagram over here, which, by the way, I got this diagram and a lot of and a bit of this information from geeksforgeeks.org. So I'll put that down in the description as well as the article that I read because it is for whatever I miss in this presentation, I'll want you guys to also, do your own research and figure out just learn more about Quicksort. So for divide and conquer, essentially what that is for many algorithms is just to split apart the data set that you are given, and then in whatever way that that algorithm is designed to sort out the algorithm, it will continue to either divide, sort, and then combine back together, or it will divide and sort, and then eventually toward the end, once everything has been divided and sorted correctly, it'll come back together. Which I think is kind of the same way of saying it, but regardless. And for quicksort in specific, pivot and partitioning is the way that it gets done. So let's go over here to the diagram. You'll see here up top, it has an array here with elements 10, 80, 30, 90, 40, 50, and 70. Pardon. So what you'll see here is that 70 has been circled. So 70 has been chosen to be the pivot. Now, essentially what the pivot is the number that the algorithm will pick in order to base its divide and conquer strategy off of. So as you'll see here, um, you'll gather the pivot, and you also notice that the pivot is the last element in the list. Now, there's some debate on whether or not, honestly, first and last, picking the first or last element in a list I believe, this is my opinion, I'm trying to base this off of what I've learned, but I could be a little faulty by saying this. But picking the first one or the last one just makes it a lot easier for the algorithm to just identify the pivot and then start sorting, to start dividing the array from the first or last element, just because it will already have the pivot. Whereas if you have it random, it could improve the average case, but it also could make it a lot harder and make the program have to go through the algorithm a lot more, making it a little bit more tedious. If I'm wrong on that one, by all means, like I said, I'll put the article down there so you guys can do your own research. But that is what I believe, that it is better just to put it. And personally, for me, I like last because that's how I was taught. So take that as you will. So going from that, so you'll have your pivot, and then from partitioning, you'll take that pivot and you'll partition a list from left and right, like from the elements that are greater than and or less than or greater than that pivot. So you'll see down here, you'll have the elements 10, 30, 40, and 50, and you'll see those sorted. And you'll see this one as 90 and 80. For some reason, that wasn't sorted. And you'll see that these are the elements that you'll partition around 10, 30, 40, and 50, and 90 and 80, and 70 would be right here in the middle. So essentially that would be sorted already. And then you'll see here, let's start over here, that after it has been partitioned, it will now pick another pivot. So it'll have 50 as its pivot. And then it'll go from there and make sure and see from right to left if anything needs to be sorted, which it does not. So it goes from 10, 30, 40, it'll pick 40, see if anything needs to be sorted from there. It doesn't. And it picks 10, 30, and it picks the last one again. So it picks 30, nothing needs to be sorted, goes to 10, nothing, and then that should be sorted already. Whereas this other side, as you'll see, 90, 80, it'll then pick 80 as the pivot, and then it'll realize that 80 needs to be to the right, no, sorry, to the left of 90, and it will then switch. the number, so swap the values essentially, and make it so that that the array will be sorted from then on. So that's essentially a brief rundown on how quicksort works. So let's go on to the next thing. So quicksort's performance, it's pretty good. So the best case is omega n log of n. And best case scenario is that when you pick your pivot, that the list is separated pretty much evenly with both sets. So the subsets will be pretty even when you pick the pivot. The worst case, however, is O n squared, which is essentially like you pick either the first element or the last element that would be sorted in the algorithm. Like best better way to put that, the least or the greatest value element of the list, and then it has to start picking other pivots, and it could go on for that forever. And that would be the worst case. And then the average case, in this case, is actually theta n log of n, which matches the base case, a best case, I mean, mainly due to just because of the pivot, if wherever it may be, it still wouldn't be n squared. It would just fall short of that to be at n log of n, and that could get better or worse depending on where the pivot would be. So let's go ahead and I'll show you guys my version. Hopefully you guys see this, my version of the algorithm. So we'll have the quicksort up here. I'm sorry, I was just checking to make sure the time I'm good on time. So here's the class. So I have a few functions in here. So this is the sort function, and this is essentially just starting the recursion of this underscore sort function, as you'll see here. And then we'll go to the underscore sort function here. And then this is if the sublist has more than one element, you'll keep going. If not, then there's no point in sorting it because it already be sorted. And from here, you will partition the list. So you'll see here that will go that I call the partition function. So let's go down here real quick to partition. So in partition, we have the parameters, the list data, the first integer, and the last integer. So the partition function picks the pivot from the last element right here, as you'll see right there. It'll initialize the index for the smaller element right here. It'll then traverse the sublist, rearrange the elements based on the pivot by using this for loop right here. As you see, a for int j equals first, j is less than the last one, and then you'll keep incrementing the j. Going on with that, if j dot compared to pivot is less than or equal to 0, it will then increment the index for the smaller element, and then it'll swap those elements. As you'll see down here, I have my swap function right here, which will essentially swap the numbers that the program has chosen, if it is necessary for them to swap places, like you've seen before with the 80 and the 90 on the diagram. And then if that's not the case, then it'll place the pivot in its correct position, which will swap, and then it'll return the index of the pivot. And then going back up here, the underscore sort will then recursively sort the sublist on either side of the pivot, and then it will just keep going on from there until the list is sorted, essentially. So from there, let's go ahead and I'll go show you guys with this test case that I've made. So I have this array. It is a very much unsorted array of all kinds of different numbers. Sorry, I couldn't get that off fast enough. Has negatives, it has a 0, and it has numbers greater than 0. And so essentially what this should do is call the quicksort function that I have made and then print the array sorted. So let's go ahead, and I hope it works because I have tested it today for some reason. And so there you go. So you'll see, so let's look for, yeah, so we got negative 42 here, and then they have the greatest number being 42. And then if we go through the list, you'll see that it continually increments. I don't believe I can scroll. Okay, good. You don't have to scroll. It'll continually increment and show you guys that the array has been sorted correctly. And yeah, essentially that'll show you that quicksort can essentially take any sort of array or list, like unordered list like this, and sort it to a correct way. That is all that I have to share with you guys for today. Like I said, if you guys want any more insight into this, I'm going to put the link of for geeks.org's article there, as well as giving them credit for the diagram as well. that's all I got. Thank you guys so much for watching.